We have mentioned MATLAB functions already. They are the extremely useful tools that you have been using since we started. Well, it's possible to create your very own functions which you can save and share with friends and family. But don't do it too much, they're probably not that interested. A function is written in an M file, but you have to use a specific format which is universal across MATLAB. Opening a function file looks like this. The first thing you have to do is declare the function, which is what the word function in blue does. Now recall how a function works. It takes an input, performs calculations, and gives an output. So now you have to specify how many inputs and outputs there will be for your function to work. The green text is what will appear in the help for your new function, and below that are notes which will only be visible if you open up the function file. Notice end, which has to be the last line of code for a function. Now we will take the loop from the previous video, which turned random numbers into binary code, and turn it into a function which gives an array of binary where we can define its length with the function's input. We can copy this code straight into a function file. Often this is a good strategy when programming. See if it works in a script, then put it into a function file. There are very few changes we have to make. We want the answer to be displayed in the command window, so we type X into the output brackets because X will be the binary array. In the original script, we had a vector with 10 columns, but now we want to be able to tell MATLAB how many we want by inputting it into the function. First we tell the function that it needs only one input, which we will call n. This is the number of columns we want for a row vector of random numbers. You must also type the name of the function here and save the file under the same name. Now we have to change the first line of code which defines x. This now means that the number of columns in x will be equal to the number n. We can also remove display x since the output of the function is x, so it will already print to the command window. The counter also has to be changed to run from 1 to n. Note that it's not possible to run functions from the editor by clicking run, because it has to have some input arguments which you type in the command window. You can see that we can have an array as large within reason as we want. You may want to suppress the function though to stop huge arrays printing to the command window. Let's make the function slightly more realistic in that it has to take an array which already exists, still of numbers between 0 and 1, and turn it into binary. So let's save the array we want to convert as data. Now go back to the function file. Previously, n was a number, but now it is an array, and we want the counter to be the same size and dimensions as n. Using length, we can easily amend our function to do just that. And instead of checking the entries of x, we are checking the entries of the array n. We no longer have to define x in the function, because this is what our input will be. Now let's run the function. You can see an array appear in the workspace with 100 elements, all zeros and ones. The function works.
When confronting a problem, it's unwise to charge headlong at it until you or it breaks, but rather plan your approach. This applies in coding as well, and the plan for a program is written in what is known as pseudocode. This follows the structure of computer code, but is written in plain English, and it helps you determine exactly what you want to achieve in your program and how to do it. We'll now try and put what we've practiced into action with this problem. Let's create a function which will plot the gravitational potential of any given point mass. First, we have to work out how to work out the potential and plot it. Then we will be able to see what user inputs are required. The equation for gravitational potential is, so we need the gravitational constant, the mass of the object, and the distance from the object. If we wish to plot the potential against distance from the mass, then clearly the value of r, the distance, will change. so we need to somehow define an array for the different distances at which we want to know the potential. Let's start the pseudocode. The inputs are mass, maximum distance from the object, and the array of distances. We know g. At the first distance, calculate the potential, and at the second distance, calculate the potential, and so on. Finally, plot the graph. Let's refine it slightly. The inputs are still mass, distance from the object, and the array of distances.
For this example, we are going to use a loop, and we want it to run from 1 to the number of data points we have, and to calculate the potential at each point.
After the loop, plot it against the distance. The final problem is getting the array of distances. This could be done by inputting the number of data points that we want as an input for the function. Then we can define the distances like this. The distance runs from 0 to the maximum distance in steps of the maximum distance divided by the number of data points we want.
We are now going to write the code in a function file, with help from the pseudocode that we have just written. So that we can demonstrate debugging in MATLAB, we're going to include a deliberate mistake. Keep an eye out and see if you can spot it.
First, give it a name and type the inputs. M is the mass, D is the maximum distance, and N is the number of data points. Define any constants and the array of distances. Then open the loop and calculate the potential at each point. Finally, plot the graph and create labels. Let's try it. Uh-oh, it's those pesky dimension sizes again. Removing errors from code is called debugging, and it can be done simply by fixing typos, but sometimes the error is more complicated, particularly when running loops. So you may want to run each loop one at a time to see when the error occurs.
There is a debugging mode in MATLAB. A simple way to access it is to copy and paste your code into a blank M file. The input variables have to be specified here, otherwise the code definitely won't work.
You then enter debugging mode like this. Enter a breakpoint by selecting a line, then run the script and the code will stop at the breakpoint. You can also see the variables saved to the workspace, which does not happen in a function file. We can now see the error. X has one more entry than V. We can solve this by making the increment of x n-1. Now run the script normally. The dimensions are the same, so the graph can be plotted. You can now copy the corrected code back into the function. This example was to demonstrate how to turn a physics problem into a MATLAB program. We also applied some of the other topics from previous videos. Hopefully, you have learned something from this series, and you might even have enjoyed watching. Now you should have a solid foundation in using MATLAB. More confidence will be gained as you continue programming, but remember that complicated problems can be broken down into simpler steps and solved with the basic yet fundamental skills that we have shown.